Welcome to After Hours Engineering. Every SoC has its processor core. And for our SoC, that's going to be the Femto. And specifically, we're going to use the intermissium variant of it, which includes interrupts. Our first task is to synthesize it so we can better understand it and then eventually synthesize it. So, let's go. We start by looking at the Femto processor itself. Starting at the top, we are on the intermissium file, and we have a bunch of flags that are going to come in handy when it's ready to use the gas assembler and the C compiler in later episodes. Here's the interface to the processor itself, and I've gone ahead and added in one extra field for debugging, and that's the halt, and that's because I've made a very slight modification to the processor by adding in the e-brake. The later versions or the more advanced versions of Femto do support the e-brake out of the box. So I've defined our reset vector to be 0 and the address width at 24. From here on out, you're going to see a lot of things that are familiar to you from Ranger, but the biggest difference is that Femto is very much a combinational based version of the RISC-V, whereas the Ranger was way more state machine based than it was combinatorial. So we have our usual, we have all of the checks for what types of instructions there are, and I've added in the e-brake version right here. So we know that an e-brake is a system instruction, and you can detect it from the lowest bit of the function 3 segment of the instruction itself. So if we just keep scrolling down here, we have our register file with write back data ALU, and in the Ranger our ALU was a single one for the most part, but when it came to doing PC addition and subtraction and things like that, we used a single CPU. Here there are some custom built shifters in there. We used the built-in ones that whatever the Toolchain decided to use. Functions for multiply and divide, which we didn't have in Ranger. Our ALUs, here's the division. And then finally here is our predicates, where we, in Ranger, we did the same thing. We determined which one of the branching type instructions. Program counter, they have a separate adder for that, where we used the ALU, the main ALU, to do that, and then routed it back through a mux. And if we keep going through here, we'll see all kinds of things. Here's the other part of the e-brake, where we had to add in, and it was commented out in the code, and I uncommented it, so that the interrupt return is very distinct from the e-brake instruction. You need this portion of it here in order to separate the two out. Without it, the MRET and the e-brake look identical. We don't want that, of course. So we needed to add this in. Here is all of our CSR stuff from Ranger, but now it's here. And they've also added in the cycles counter, which we didn't do, but you can. This will count the number of instructions or cycles that the processor's been through since it was powered up. And then if we keep going on down here, we'll see here's our write back. We determine which instruction it is and whether we're going to do a write back. Then we come down, here's our load and store, and just like in the Ranger, we looked at whether we were loading a byte or a half word or a full word altogether. And then here is the core of the CPU itself, and that is the state machine. And you can see that it's considerably smaller than Ranger's. There originally was only 4 such states at a maximum. Not all of these are activated at every single one. And I've added an extra one to support the e-brake, which means my state bumped up from 4 to 5. And then I added the matching bit for 1-hots. And there we go. That's pretty much the system or the modifications, except for this one section right down here. I added in the system state for the e-brake, and I added this one little line up here that says if it's an e-brake, then set our next state to be the system brake. And that's it. That's the Femto in and of itself. If you removed all the comments and everything, you're probably looking at 200 or 300 lines. Next is the top module, and as you can see, it is as simple as it gets. We have our SoC that we'll take a look in a second, with its input clock coming in from the test bench, and then a fake port. This is just simply so we can see it in Verilator and see that it's been written to. Again, our intention is to see if Femto is working and we've correctly set it up. So now we come to the core of the thing, and that's the SoC itself. And in the simulation, it's pretty minimal. It's so minimal that we're looking at just the port, and that's it. We have the usual signals that we'll need for the Femto itself. We're routing the clock straight through. It's coming straight from the test bench. LEDs are pretend. They're not really real. We're going to be looking directly at the port itself. And then we have our RAM. We are going to do 65K bytes, and we'll divide that by 4 to get the number of words. So this RAM will be 16K of words. We have our dual port RAM right here. And then above we have the writing to the I/O address, which would be the LED ports, which is at 0. Then we have the initialization. Here we're loading in the program that will execute, and it's defined in firmware. And then finally we have the processor itself. There's all the signals that go into it, our halt flag that we have added to the Femto, our little tweak, and then the rest of this is just minor state machines for resetting the system, and that's it. So there's our SoC. So let's take a look at the firmware to see what it's going to do. Here we are in the firmware, and the only thing we're going to do is write 99 to the I/O port and then turn around and write it to a memory location. So we load X1 with 99. We then load X2 with the base address of I/O. If we come down here, we can see the 01, there is the base address. So if we come back to our SoC, we can see that all I/O starts at bit 22. If it's high, then we know we're talking to anything in the I/O range. If it's low, then we're only talking to RAM. And there you have it. So if we come back into the firmware, we're going to assemble this and run this little program, and here's our new fancy modified e-break statement, which should cause the processor to halt in the simulation. So here's the firmware. We can see that it's correctly compiled everything, and we're ready to run the simulation. So to kick off our simulation, we'll run over here to our folder for simulation and run the make file, and there pops up the simulation. So let me collapse the terminal. And there we have it. There is the Femto operating, but let's make sure that it is. So we have our state, and just like the Ranger, it goes through its sequence of states. And as you can see, it's a lot less states in it. It does a fetch, a wait, and execute, fetch, wait, and execute repeatedly. That's good. We also have the instruction register. Our PC counter is incrementing by 4. Excellent. That's good. Write backs are happening because we're executing certain instructions that perform write back. Some don't, like a store to I/O is not going to do a write back, and that's what we expect to see. Again, the instructions are down here on the RAM R data. We're reading data out of the RAM, and here they are. Excellent. So we have our memory addresses, the write masks as to whether we do it, and here, because we're dealing with bytes in this particular instruction, the mask goes to a 1. Excellent, that's expected. We're determining whether it's a load or a store. Yep, it's a store right here. So we go to 99, it's storing it to the I/O address. That seems reasonable. We're not dealing with any branches or any ALUs. We expect the processor to halt when it hits our e-break. We'll scroll over to the right in a second. But what's important here is the port. We want to make sure that our program writes to RAM or to the I/O port, and sure enough it has. There's the 99 that we were expecting. So let's scroll over to the right to see the end of it, and as it's going through the instructions, eventually it hits our e-break that we added to the Femto, and in our case it goes into the ubiquitous black hole and stops permanently, and we set our flag to a halt. Excellent. In the future episodes, this e-break will become the mechanism that will send us back to the monitor, whether we do a Control-C to break or the program simply reaches a stopping point. We don't want it to just lock up our SoC. We want it to go back to the monitor. But for now, halting is perfect. That's what you have. So the simulation seems to be going just fine. However, there's one thing that you may have noticed if you were paying attention, that the instruction register doesn't look right. I mean, certainly the CPU is running, but the instructions are all mangled up here. And the reason for this is because Femto only looks at the top bits. It ignores the bottom 2 bits. And effectively what you have is a shift effect. So if I bring up my calculator here, and you look at our first address down here, which is 28048 or 4083, we take that and shift it right 2 places and then convert that back to hex, we get A01020. And sure enough, that's what we get in the instruction register. That's when I started working with Femto, I was like, there's something wrong with this thing, but yet it's actually running the program. And that's when I realized that the Femto in most of the code is ignoring the lower 2 bytes. So yay, the simulation is working. It looks like we've successfully implemented the Femto SoC just enough to get it to work by loading RAM and setting up some memory mapped I/O. So now we're ready to take a look at the synthesis. For synthesis, we'll look at the top module first. And this is where the hardware comes in. So we have a 48 megahertz crystal coming in, an RGB LED in the upper left of the board, I'll show you in a second, and we have PMOD A. The Schoko, as we've seen before, actually has 2 PMODs, PMOD A and B. We're only using A. And then we route from the SoC over to those actual pins out to PMOD A. So we should see the lower bytes show 99, which is 1001, 1001. And there's the SoC as it is. In this particular synthesis, I decided just to cut that 48 megahertz down to 10, but there was no reason to. I just decided to do it. The Femto will operate higher than 48 megahertz, but I just thought I'd play around with the PLL in this case. In the SoC itself, we have our usual signals just like we had in the simulation, but this time we have an actual PLL that is not being rerouted. It's actually coming out as approximately 10 megahertz. The real LEDs, slightly less RAM just because ECP5 does have a fair amount of RAM, but not a whole lot, and this is 16K words, so it's actually 64 kilobytes. And then we have our RAM, much like it is before, only it's really combined into one. We initialize with the firmware, which we reviewed in the simulation. And then down here we've set a couple of the flags or signals into the Femto as constants. The reason why is that the RAM is fast enough so there'll be no waiting or busy flags when it comes to reading or writing from it. The interrupt we're not using right now, we will eventually. And here is the Femto in and of itself. And then the rest of this is just a reset sequence for controlling the SoC itself. Nothing much there. So let's go ahead and crank up the terminal here. So I'll bring that up and we will go and run make. Now while make is running, we'll bring up the video image of the actual Femto. So we'll get that kicked off there and then we'll bring up the board. And so you can see here that the board is off. Let me turn it on before it actually starts running the JTAG here. There it goes. Hopefully it'll prepare. Once it goes green, now it's ready. And there it goes. It's being programmed. And there it is. So the tiger is over there in the top, and there's the blinking red light right there. And the 2 PMODs, PMOD A is over here on the lower leftist side, and PMOD B is in the upper right. And then if we follow the wires from PMOD A, we go over here to the breadboard, and there you have it. The processor is actually executing because it stored 99 out to port A, so that's 100110001. Excellent. So synthesis is working as well. So we now have a fully functional Femto executing instructions from our simulation and from our firmware. Excellent. As a final note, one of the more important things with this SoC is the memory map feature that we're going to use. We're not using a complex bus like a Wishbone or AHX. We're just using simple memory mapping. And we had seen that here in our SoC itself. We have whenever we know we have I/O, we know that bit 22 is high. And over here, bit 22 is 400,000 address. There's port A. We know that if it's not set, that it's RAM. So it's everything down below here. So right now, we're consuming a chunk of memory just for RAM and a few for the I/O. And eventually, in the next episode, we'll have the UART come in. And that's what all of this code does. We build our RAM here. We have our dual port inference going on here for the block RAM. And we have the port itself. So you can see here, we're checking to see, is this I/O, which is bit 22? Yes, it is. is at a word address 0, which means we're at port A, so the lower 8 bits is different than what Femto does. Femto uses 1-hot encoding to define its devices, and I'm using linear addresses. And if it's I/O and it's address 0, then that means we move it over into port A, and that's exactly what this is, 4000. When we add UART, we're going to add more stuff here, code, in order to differentiate that from port A. So it'll start at address 400,001, and there'll be 3 registers or 3 addresses within the UART, and we'll see that in the next episode. Excellent. We now have the core up and functioning. So what's next? Glad you asked. It's communications. And hence, we need a way to interact with our SoC, and we're going to do that via UART. And this means we need both hardware and software, at least enough to establish connectivity and verify towards our FPGA. So until next time, peace!